All right, welcome back to Mr. Hong's class. Today we're going to be talking about 2-4, which is the last section of the unit. And today you will be able to analyze the effects of changing the absolute value function. So what that really means is, let's say for example that hmm, okay, let's say for example I have a picture, right? Like in my house, like on my wall. And like this is me, and this is my family. Sure, whatever. But what if that picture became like this? Wouldn't you say that, oh, like, you need to, like, you need to put pressure right here so that it can move to be corrected so that it would be, like, straight or, like, level? Or what if I wanted to move the whole picture? Because I didn't like it where it was in my house, and I wanted to move it, like, from the living room to the hallway or something in my house. So we can talk about that like the same way about graphs. As in, I have this graph right here, this absolute value graph. And let's say, for example, I don't want it to be here. I want it to be like here. Okay, but how do we do that? Today, you're going to be learning how this happens and what the formula or like what the equation looks like and what the graph looks like and like how they relate to each other. So you know that every graph has an equation, and let's say this vertex right here is 2, 1. Then it would be absolute value of x minus 2 plus 1 is equal to y. But yeah, we're going to be talking about what affects the graph. So we already know that we have the parent function, which is f of x is equal to absolute value of x. Know that the parent function, that word pretty much means the most basic type of the function. So this is the most basic type of absolute value function that you can have. All right. So vertical translation. So I know that everyone here has taken geometry, but if you forgot, it's okay. But translation means movement. As in my picture, I move my picture from like the living room to the hallway. My graph can move up, down, left, and right. Vertical is talking about moving up and down. So the way that we do this is by writing it like so. The k, or like the variable that we use, is kind of like the y-intercept in your slope-intercept form equation, where your slope-intercept form was y equals 2x plus 2. You knew that this graph would move up 2 units, like right here. That's 0, 2. And it would just be like this, right? It moved up 2 from like here, which is like this is just 2x right here. So when k is above 0, which means it's positive, that pretty much we're moving up k units. And that really means, like, for example, the example below us, y equals absolute value of x plus 2. We're moving up 2 units. And know that units is just like in the graph where you just go like this. 1, 2. I guess I'll draw this different color. All right. So if if it's positive and it's making my graph go up, if it's negative, like so, k is less than 0, which means it is negative, that means that it goes down k units. As in, y equals to absolute value of x minus 3. That means I'm going down 3 units. It looks like so. This will be, so I use this color, opposite side of the spectrum. So down 3 units from the original, right? So from here, 1, 2, 3. And I'm gonna actually use my line thing this time because my lines are bad. Boop. And boop. Nice. So here we learned the vertical translations and how it applies in our function, which is outside of the absolute value, but the same side of the equal sign. So if we have up and down, which is talking about the y-axis, we can also move it left and right. And once again, translation means movement. And horizontal means to, I guess I should write it in English. Left slash right. When I see the word horizontal, I think of the word horizon, which is kind of like the ocean horizon. Like you can see the line going left to right. And the way that it's written is kind of weird, and I want to write some special notes because this will be pertaining into most of our functions later in this year. And I want you to think of horizontal as, think of it opposite. We also notice that this h is inside of our absolute value. And the reason why that makes sense, let me pull out Desmos. And the reason why that makes sense is because what if I wrote y equals x, which is our regular like linear equation, right? And y equals x minus 2. You see how this went a certain direction? Is because my x is in parentheses. And it's being subtracted by 2. But look what happened. It went to the right. Or we would think like, oh, like minusing is like going towards the negative side. But for the horizontal side, it's opposite. As in, me subtracting 2 from x actually made my graph move the right direction or the positive direction. So when h is greater than 0, such as like x minus 3, we know that we go this way. H units. And the reason why it looks opposite is because the base equation right here. The base equation right here. This will always be the same. So the reason why it looks like y equals absolute value of x minus 3, 3 is h. That is equal to h. H is equal to 3. Because we know that this part right here, this is part of the equation because it is like so. But the 3 is equal to h. So we go to the right 3 units. So we go to the right 3 units. And that looks like so. This one's like the seaweed color that I like. Just here. And I will draw it like so. 1, 2, 3. bada bing, bada bing. Nice. So if h is greater than 0, our line moved horizontally to the right or to the positive direction, h units. So if my h is negative, this is positive, that means that my graph is going to go the opposite direction, which is to the left, h units. But look what happened to my equation. from like eyes meet, we can see that it says x plus 2. So we would always think like, oh, like positive, if it's adding, it should be going to the positive direction. But really, this equation right here is saying y is equal to absolute value of x minus, and I got this minus from my base equation, which is the same as like here. And that's from our base equation. But if I want to subtract something to get negative 2, so let's say like z minus a number is equal to negative 2, let's make the z is 0. 0 minus something has to be negative 2. That's 2, right? But what about 0 plus something has to equal negative 2? Wouldn't this number have to be negative 2? Yes. So I can really say that a number subtracted by a negative different number, which I'll write as a star, is equal to number plus star because of a double negative. So here, you see how like this has a plus sign and this also has a plus sign? I can assume that this is a double negative, which is true. So it's negative 2. And this is where we find out, oh, this is where my h is right here. So this is my h. H is equal to negative 2. And that's why it goes towards the negative direction, because of my h is equal to negative 2. Not because my equation looks like it's positive 2, but because I know, or you will know, that the base equation is x minus for the inside of the absolute value. So what that looks like is like so. I think I used like this maroon color. Yeah, I did. I won't use that color. I'll use like this yellow, like this limey lemon color. Negative 2, which is right here, because I went 1, 2, and I just draw my absolute value going a slope of 1. There we go. So we learned so far the translations, which is movement going up, down, left, and right. So pretty good so far. And now we have some stretches, compressions, and reflections. And this is also known as your slope. So when I come back to here, you know that it is y equals mx plus b. And this m right here, that is talking about slope. And we know that the slope really means the rate of change. But it only works, like the slope is like considered like only applicable in line graphs, kind of like linear because it is a line. But with like graphs that have like funky shapes like a U or a V, which is like absolute value, or like a squiggly, we can't say like the rate of change is true for all these. for all the time because we know that the slope is different from like this section and this section. So instead of saying slope, we say vertical stretches, compressions, and reflections. And think of it like when we have like a compactor, uh, trash compactor. What the? That smashes. What the? But you know, like those machines where they have like this pedestal, like they have like this pedestal like right here, right? And you put like an item, you put an item here, and there's like this big like hammer thingy that like comes down and it smashes this thing in half. This is vertical compression because you're smashing something. And when you smash something, what can I grab near me? I don't want to waste a cookie, which is near me. Okay, let's grab this receipt. So if I have like this receipt right here, and you can see like it's flat right now, but if I like fold it up, it'll kind of be like bigger, right? Like it's not completely flat now. So when I vertically compress something, watch what happens. When I vertically compress something like so, I'm like flattening the top and the bottom. But what happens to the left and the right of this? My my receipt, like my wad of receipt was like bigger. It was like so, like it was skinnier. But when I compressed it, it became really flat and it spread out left and rightward. As in like if you like squeeze like a fruit gushers, you know, like it gets flat and then like it spreads. So the same idea comes from this. Vertical stretches and compressions. The vertical stretches, think of it like this band that I used for my hair whenever I had long hair. If I would stretch it like vertically and I went like this, wouldn't it like make my rubber band like more skinnier if I kept stretching it over and tighter and tighter? Yeah. So when we talk about slope for absolute value or anything else that has like funky weird lines that don't have the same behavior as linear, we have to call it vertical stretches, compressions, and reflections. Well, reflections, we already know what that is. And vertical stretches, the key component is that the number is outside. It is outside and it's being multiplied. Kind of like multiplied. Whatever. You know what I mean. That's kind of very similar to like this. Isn't my slope being multiplied by my variable here? Yes. So the same thing applies here. But my slope is being multiplied and it's outside of my absolute value. So when a is greater than 1, or the absolute value of a is greater than 1, we can say that it is a vertical stretch. And that's because if my a is greater than 1, that means think of it like a slope. If my slope is big, then like my graph gets like steeper. So y equals 2 to the absolute value of x is vertical stretch by a scale factor of 2. And I'm going to make this yellow color again. I kind of like this color. And I didn't have any translations or anything, right? So I would still start from 0, 0, but I would go up to the right one, up to the right one, and so. And then obviously I know that this is like this is symmetrical, so I just copied it. Be like this. And I'm just guesstimating. But yeah. But what happens if my A is like -4? Doesn't my graph still gets steeper, but is just facing a different direction? Yeah, we're gonna be talking about that very soon. Let's look at the next part. A is greater than 0, but it's less than 1. As in A, absolute value of A is a fraction or a decimal or whatever. It's just smaller than 1, but greater than 0. As in, for example, 1/2, 1/3, 5/7. It doesn't matter. As long as this number is less than 1 but not negative, as in it is a fraction of a whole, it's considered this. A vertical compression. And let's look at the example and I'll explain why. Or why we name it that and what happens. So y is equal to 0.5 or half of absolute value of x. This is a vertical compression of a scale factor by 2. And the reason why we write it like this is because it's getting twice as flat as it was before. Because how many of these does it take? How many of my scale factor does it take to get to 1? And that's 2. It takes 2 halves to make a whole. Don't worry, this part right here, we're going to be talking about this a lot more, and to be frank, we don't really ask it to be written like that often, but it's important to know. So, if I go back to Desmos, and I write that equation, which is right here. Get out of here. 0.5 absolute value of x. You see how like this graph got kind of like fatter and well compared to my absolute value or my apparent function, my green graph is flatter than my purple graph, which is my parent function. And that's because I like smashed it from up and down. As in I compressed it, and compressing means pressing, like smashing. Obviously stretching means pulling. So it would make sense that this would be like a bigger, like a wider version. And I know that my slope would be like I would go up a half and I would go to the right once because of algebra 1. Hopefully you know that because of algebra 1. And I'll be using this seaweed color. Another one of yeah, I'll use this color right here, this creamy color. So once again, we start from the origin because we had no translations. So we go up 1 to the right 2. 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 Well, to the left 2 for the negative side. There we go. And we have one last thing to talk about. What if A, not my absolute value, but my regular A is like -2 or whatever, or -1/2? What happens? And that reflects on the the x-axis. pretty simple, right? Because look what happens to my Desmos graph. What if I just make my green graph right here? What if I just make this negative? Boop. It just flips. Like so. So I can just draw this graph. And I'm going to draw the graph -2 times the absolute value of x. And I will make this... I don't know how to find like this nice pink color. Ah, there we go. Okay, so once again, we're starting here, right? We're going to right once, down 2. Because if I apply like my rise over run, which still applies, but we just have to do it separately. We know that I'm going down 2 because it's negative, and I'm going to the right 1 unit. Like so. Nice. So we learned vertical stretches, compressions, and reflections. Just think of it as like this rubber band. If I stretch this rubber band, even if it's like a circle or whatever, I can pull it on the top and the bottom because vertical is talking about up and down. My graph got skinnier, or my rubber band got skinnier, right? But if I pull it from the left, or whenever I try to press it down, as in if I try to flatten it, you see my my rubber band got wider. So that's pretty much it for the vertical stretches and compressions and reflections. One last key concept that we have to talk about before we conclude this unit, and that's going to be the horizontal stretches, compressions, and reflections. And I want you to think of this as the opposite of vertical, which is true, right? Because going horizontally and going vertically are opposites considered in Algebra 2. So think of this as opposite. One key thing that you need to know on the test is that the b, like the scale factor, is inside. It's inside absolute values, like the absolute value equation. If the absolute value of v, the absolute value of b is greater than 1, then it is actually a horizontal. B is greater than 1. It is a horizontal compression. I believe it's so. And let me check my work because I gave you an example right here. It is. And the reason why is because we're using horizontal, so we're talking about left and right, right? Like we're talking about the horizon. And compression means smashing or like pushing towards. So if I have this rubber band again, and I press it in like so, I press it left and rightwards like this. If I flatten it like this, then my my rubber band is becoming elongated up and downwards or vertically. So my graph looks very similar to this graph right here. This graph right here, my green graph, which I will write again. I guess it's like a yellow. And look at the difference between y equals 2 times the absolute value of x and absolute value of 2x. They look very similar. Because they are because they're taking the same operations, different order, but for absolute value and multiplying, the order doesn't matter that much. So I would just draw the same graph as I did before. Okay, so if this is horizontal compression, that means my other one is gonna be a horizontal stretch because of process of elimination. We know that horizontal is opposite of vertical, and we know that compression and stretches are opposites too. Or I hope you noticed that. But yeah, if the absolute value of b is greater than 0 but less than 1, or if it's a fraction or a decimal or not a whole number, not greater than 1, it is a horizontal stretch. And the stretch looks like this. As in, I'm pulling it. I'm pulling it from the horizontal side, which is left and right. So I'm pulling it like this. And I guess I'll graph it. What do I graph this one? Like this cream color. Looks like a very pretty eyeshadow color. But it looks like so. Go up 1 to the right 2. Go up 1 to the left 2. Nice. Okay, sorry about that. My house was getting a little loud, so I told them to shh for y'all. You're welcome. And the last one is b is less than 0. If I noticed from my earlier example, if my a, which is my outside number, my outside scale factor, became negative, it reflected over the x-axis. So what is the opposite of reflecting over the x-axis? Or I guess what's the opposite of x-axis? It is the y-axis. So resulting in this must mean that it is reflecting, because we know that if this is negative, then I know for sure it's reflecting. But we don't know which axis, but we just use process of elimination. And let's try it out. Let's graph this right here. Y equals absolute value negative x minus 2. So it looks like so. But what happened? Which one do we do first? Do we reflect first or do we move first? And I'm going to say, this is a key thing right here. Always do all translations and scale factors before reflecting. And that's because if I reflected it over the y-axis whenever it was just here, y equals absolute value of x, it wouldn't have gone anywhere. But if I did y equals to the absolute value of x minus 2, which I know that I learned recently that it is going towards the opposite direction of what it looks like, which is going towards the positive direction, it looked like the purple graph reflected after I applied my transformation or my translation, which is true. So let's draw it. What did I draw this one as? Pink color. Like so. And then I just use my line tool. Like so. I graphed that really fast because I knew the slope was still 1 because there's no number in front of my x. Well, there's a negative 1, but imaginary. So in conclusion, we learned on this page the vertical stretches, compressions, and reflections, and the horizontal stretches, compressions, and reflections. So in summary, what really happens is that we get like this formula thingy. Oh my gosh. So what happens is that everything inside is going to be talking about the inside right here is talking about horizontal. and everything outside, inside the absolute value to be specific, then the outside is talking about vertical. As in my, you know that my A and my K are outside, so they are vertical. They're changing the vertical like characteristics of my graph. So to find the vertex, remember how I told you that the vertex was kind of like the meeting point of the two halves? As in like the vertex is right here for my pink graph. And my green and my blue graph are right here, and also my parent function is here. My vertex are all in the middle, which is 0, 0, or the origin. So how do I find the vertex of this? And the equation is actually pretty simple. It tells us in this equation right here, which is HK. And that's why this form right here is so good for you. You always want to have it in this form if you're going to be graphing it, because it is called vertex form. This is where the name comes from, because it gives you the vertex for free. You have to analyze it yourself. I want to write one thing here. The line of symmetry is x equals h. As in this h and that h are the same. Because my line of symmetry has to be where my vertex is, or it doesn't make sense, because my crease would have to be like, my crease would have to be not there. My crease would have to be like here for my pink graph, right? Doesn't that include my vertex right here? Yes, it does. So you see how like this x value right here is -2? So for my pink graph, my pink graph, the line, I'm gonna write LOS. Line of symmetry is x equals -2. And we have to write it like this, kind of how I told you from last section, is because this is a line. X equals number is a vertical line. As in all of these values on this line have the same x value, which is, for this situation, -2. So yeah, this form is really, 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 really useful, and I'm going to show you how I use it. Boop. So the reason why I talked about it there is because I didn't want this on this page. So what are the graphs of the following? How are the graphs different from the parent function, which I wrote right here? If I look at my notes from before, I'm talking about an outside number that's being added or subtracted. So I would have to go to my notes and find something that is outside, added, or subtracted, like my examples. So these are all inside, these are outside, but they're being multiplied. Ah, here it is. Something is being added outside. So I know that since this is being subtracted by 3, this is going down 3 units. So this must be going down 4 units. And this answer right here is more than good enough for me. Like the arrowhead and a -4 pretty much tells me that you know that it's going down 4 units. Like so. 1, 2, 3, 4. And I completely missed that order pair, but whatever. You're fine. You know what I mean. What about this one? This one is being added inside my absolute value. So I have to find something that has adding and subtracting inside. Oh, look at this one right here. Y equals to absolute value of x plus 2. But I wrote it like this because I know that my base equation is x minus. So it created a double negative to make a positive. So do I go to the left or to the right 2? according to this, it looked like I went to the left or towards the negative direction by the same amount of units, 2. So if I have 1, that must mean I must be going to the left 1 unit, which will look like this. And then I just draw my absolute value function, like whatever. This graph isn't into scale apparently, but yeah, like so. Nice. So I want to do this one for you because this has 2 things. It has a negative scale factor, and scale factor is outside. So there's 2 key things that I need to be talking. I guess I shouldn't use the arrow key because we're talking about attributes. I'll use an equal sign. So I have a negative that's outside, and I have a 2 that is outside. If I locate that, oh, it looks very similar. Oh, it is this right here. So I'm reflecting over the x-axis, and I have a positive number being multiplied that's bigger than 1, or a negative number that's being multiplied that's bigger than 1. So it must be a vertical stretch by a scale factor of 2. So how would I write this is reflect x-axis and vertical stretch by 2. And it looks like so. I would first, like, I guess I should write the steps first, or the way that I would do it. So I would draw this, right? And then after that, I would make it the opposite, or like I would flip the signs of this. So this is what, 1, 2. If I flip over the x-axis, that means that my y's become negative. So now it becomes 1, negative 2. And so on and so on. And now I just graph this one. Oop. I drew that. This is not a good point. This is the point. So this is the before reflection. As in, I did my transformations and my my stretches and compressions before I applied my reflection. Okay, this last one right here, which is y is equal to the absolute value of 5x. This is inside and being multiplied. So if I look at my graph or my table or my thing, whatever I drew, it's inside and it's being multiplied by a positive number like so. So it is a horizontal compression. Oh, I have the space right here. I'll write HC for horizontal compression by 5. And horizontal compression is like this, right? Like smashing from like left to right and like pressing like this rubber band going inward like this. But isn't like doing this the same thing as pulling it from the top? It's really the same thing. So pretty much my graph has a slope of 5, as in 1, 2, 3, 4, 5, 1. Like so. Nice. So this is outside. Oh. This is outside. And it's between 0 It's between 0 and 1. So this is a vertical compression, as in it's making my graph chubbier. It's a vertical compression. And I would do it like this. This is actually like 4 over 10, which is equal to 0.4, which is equal to 40%. So I'll go up 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. Oh, I can't do that. I can do 2. I can do 2, 5. 1, 2. 1, 2, 3, 4, 5. Like so. And watch how I'm gonna write this. Horizontal compression. Not horizontal compression. Sorry. Vertical compression of 0.4. That's it. This one's inside. It's inside, and it has a negative. So I know for sure that if it's inside negative, it is going to be reflect y-axis, and it's going to be scale factor of 0.25. But whenever remember how I told you that whenever we reflect over the y-axis, absolute value of x, and I do like the y equals to absolute value of negative x, we know that taking the absolute value of like 5 and taking the absolute value of negative 5, they're both equal to 5. So they're really the same thing. So I can really just say that I don't really need to worry about this negative sign. I can just graph this 0.25x, which is 1 over 4. As in this is rise over run. So I would go like this. 1, 1, 2, 3, 4. 1, negative 1, 2, 3, 4. Like so. Nice. So this is a 0.25x. Yeah, this is a horizontal stretch because I pulled it from the left and right by 0.25. So without graphing, as in if I look at this function, like this equation, I can get a lot of information. Really all I gotta know is my HK, which is this number, this is my H, and this is my K. Just this 2 is my H. Just this 4 is my K. If there was a minus 4, then it would be negative 4. So my HK is 2, 4. Not negative 2, 4. Positive 2, 4. Because my base equation is y equals to A times the absolute value of x minus h plus k. You see how the base equation says x minus? This has an x minus. So h must be 2. So the vertex is hk actually, which is equal to 2, 4. Nice. Another free one is the axis of symmetry, which is x is equal to h, which this turns into x is equal to this 2 right here, 2. So usually for min and max, I give you an interval, but for this question, I didn't. So we can assume that we're talking about the maximum range and the minimum range. As in, isn't this really like my range right here? So my range would look like this, right? It would normally look like this if I was just talking about my range in total. So what is this value right here without graphing? I know that this graph is facing like this because there's no negative in front of it, right? There's no negative on this 3. So I know that my lowest point is going to be right here, my vertex. What is the y value of my vertex? Oh, it's 4. But what about my max? I have 2 arrowheads facing upwards, so my maximum is actually infinity. X-intercept, Y-intercept, these are pretty hard. And the way that you do this is by um, making y equals 0 and making x equals 0 respectively. As in, you're making the opposite variable equal to 0. So we can do that. 0 is equal to 3 absolute value of x minus 2 plus 4. And then we would have to do the math. Um, we're gonna skip that for now. We're gonna be practicing that more later. Actually, dude, I'm your teacher. I should do it. Zero is equal to 3 times absolute value of x minus 2 plus 4? Bada bing, bada boom. So this is why section 1 and section 2 were super important and why we did that first. Because our first step, or our steps are get absolute value alone. And it's not alone because there's things to the left and to the right of it. So I need to get rid of it by using PEMDAS, or opposite order of PEMDAS, which is negative or minus 4. Subtract 4 is equal to 3 times the absolute value of x minus 2. Then divided by 3, right? What happened? What happened? What happened? Where am I? Ah, there we are. So negative 4 over 3 is equal to absolute value of x minus 2. So that was step 1 right here. Step 2. Positive and negative version of the opposite or side of the absolute value. But what's wrong with this problem right here? Let me give you some time to think about that. What is wrong with this problem? What's wrong is that this is a negative. This cannot be negative. Because this, nothing I can put inside here will make this negative because I know everything that comes out of an absolute value is going to be positive. So this is no solution or not available or not applicable. And I'm gonna show you that by graphing it later. So pretty much I'm saying that I don't have any x-intercepts, which is perfectly fine. Okay, let's try the x-intercept. So this is y is equal to 3 absolute value of 0 minus 2 plus 4. So this becomes negative 2. This becomes 2 times 3 plus 4. This is 6 plus 4. Y is equal to 10. Nice. Where is it? Oh, here it is. So this is 0, 10. Is it 0, 10? Yeah, it is. 0, 10. And let's try graphing this now to check our answers. So the 3 was outside, minus 2 plus 4. So it's all the way over here. So what I really want to check is my x-intercept and y-intercept. Those are the most interesting. So let's look at our y-intercept, which is here. Nice. 0, 10, I got that right. But how come I don't have an x-intercept? The reason why is because my graph went upwards away from the x-intercept. So my graph actually never touches the x-intercept, and that's perfectly fine. And that's why no answer is an acceptable answer. My lowest point was 4 on my graph, which is here. Nice, 2, 4. My maximum we can't calculate. The axis of symmetry is my vertex, which is x equals to 2. So if I write x equals 2, you see how this black line cuts this line in half? That is my line of symmetry. And then my vertex is right here, 2, 4. Nice. So this is a very challenging question right here. If anything, this would be like a bonus question. Maybe I would make this a test question if I feel like we have enough time to go over it again. If you want to, you should try this problem because this problem is very similar to something that I would be writing in the test. But I'm going to end it here. Today we learned like all these things that can change our absolute value function. How can move it up, down, left, right, make it fatter, make it skinnier, vertical stretch, vertical compression, reflect over the x-axis, reflect over the y-axis, and we applied it by looking at a vertex form equation for absolute value and telling you, like, deciphering all that information into like all these facts, all these attributes that we can tell just from the equation without graphing. And that's what's really important. You need to be able to get that skill to look at something and be able to interpret a lot more things. And that's why I like math, because it helps you train that skill. But this is the last section of the unit. Besides this, we're going to be taking our test soon, but we're going to have to review. So I'll see you at the review. Later, guys.